started. Now I leave the floor to Ali Peker.
Merhaba herkese. Ali Peker ben. Gizem'le beraber, Gizem Ezgi Taştan'la beraber biraz birlikte çalıştık. Gizem, TED Üniversitesi'nde mimarlık okumuş. Sonrasında özel sektörde de yazılım alanında da tecrübesi var. Şimdi matematikle ilgileniyor. Şimdi de yaptığımız çalışmayı size anlatacak. Buyur Gizem, söz sende.
By the way, in this presentation, we will utilize Copula Functions to understand the relationship between two different time series. But before getting into that, I will also explain why using the traditional correlation coefficient does not work well in time series also. And after presenting the Copula function, especially the Gumbel copulas, we will also add another layer of confidence that is known as conformal prediction too. Conformal prediction is a statistical method, and even though it is not widely used in machine learning applications or machine learning algorithms, I hope its usage will increase from now on the grounds that it will provide us a certain confidence interval, which guides us to decide whether the risk is worth to take or not. So let's start with the time series and its properties. A time series is a sequence of chronologically ordered data points. And this chronological order allows for us to identify the trends, seasonality, cyclicality, and irregularity. Trends means that long-term movement in the data, it indicates a general increase, decrease, or stability. And seasonality means that it's repeating patterns at specific intervals, like daily, monthly, or yearly. And cyclicality, unlike seasonality, cannot be predicted beforehand very easily because it can change very easily. And when it comes to, let's also mention the irregularity part, it is somehow some variations which are not systematic or repetitive. So let me show you one example that is related to this topic. So these are two different time series. The blue color shows the price of the zinc, and the orange one shows the company's positions according to those the change of the price of the zinc, let me say. So in this part, we will see how companies adjust themselves according to the market positions. From the beginning of 2020, we can see that the price of the zinc increases. So also there exists another increase in the positions. And after, from that point, the zinc prices reach their peak. And also, probably we can sense that the companies had a tendency to expect this prices will be downwards afterwards. And at this point, at the beginning of 2022, there is a downward trend in this part. So maybe we can say that the companies probably expect the values of the zinc to be decreased. Okay, so there's a question. Do you think that these two variables are related? Well, of course they are, but how we can compute, how we can calculate these type of relationships? And I am well aware of the fact that the correlation coefficient is a widely used method to understand the relationships. And the correlation coefficient quantifies how changes in one variable are associated to other changes in another variable. For the n sample size, the Pearson correlation coefficient is calculated like this. So these are the means of x, means of y, and this is the standard deviation of x and standard deviation of y. And the correlation coefficient ranges from -1 to 1. So as you might infer from this image, when the correlation is 1, it shows a perfect linear relationship between these variables. And when it is a negative, highly correlated relationship, let me say, they behave just like the inverse, but still with a linear relationship. So there's a question, is correlation a viable metric for time series analysis? So let's consider two trending time series, just like this one. Even though they're not related because this is the UFO sightings, still their correlation is really high because of the linear dependence. Conversely, if two highly related events may have a very low correlation coefficient due to nonlinear dependencies. So it seems that in time series, especially, using this correlation may not work well. So in order, so we can, so let me introduce another function, a function known as Copula, and its theorem belongs to the Abe scholar in 1959. And it says that let x and y be continuous random variables with marginal distributions f of x and g of y. Therefore, the joint distribution function h will be defined like this. So a joint distribution function h describes the probability that two random variables x and y simultaneously takes on values less than or equal to x and y respectively. And then the theorem continues like this. There exists a function, Copula function. Copula function is a coupling function, by the way. So as an input, it takes marginal distribution functions, and as an output, it gives us the joint distribution function of those two marginal distributions. And furthermore, if f and g are continuous, the copula C is unique. Otherwise, C is uniquely determined on the range of f multiplied by the range of g. And let me also mention some properties of copula. For every x and y, let's consider the point I cube with this coordinate. So maybe you can also sense that the first two is the marginal distributions, and the second and the third coordinate corresponds to the joint distribution. So this mapping from I squared to I is a copula, and a two-dimensional copula is a function that has those three types of properties. So the first one is known as the grounded property of a copula, and in the second one, we can say that when the correlation is one, so when one of the variables marginal distribution is one, the output will be depend on the possibility of the other uncertain event. And there is also another properties of the copula known as the C volume of the copula. So since a copula is a distribution function defined on the unit square 1 to 0 with uniform marginals, we also have such a property too. And this is an example of a Clayton and Gumbel copula. Even though we will only talk about the Gumbel copula, I also want you to somehow understand how they look in the third dimension. So this shows the upper tail dependence, and this is the lower tail dependence. Clayton copulas are known for their lower tail dependence, also known as the left tail dependence too. And especially in taking risks, especially in finance or modeling the risk, let me say, we will use Gumbel copula because we will learn its reason why. So maybe you might ask, what is the boundary that we can model with a copula? And this is known as the M copulas and W copulas. W copula is the lowest boundary of this dependency, and M copula is the upper bound of this dependency. So I have a range of dependencies that my copula can model, but they must be bounded by M and W copulas. And as you might infer from this image, there exist many copula families. But as I just said, we will also focus. We will only focus this Gumbel copula part. So it has a upper tail dependence. Clayton has a lower tail dependence, and Frank copulas doesn't have any tail dependency. Maybe it might be useful for you to see such an image. So let me start with the Archimedean copulas, because Gumbel copulas are considered under the title of Archimedean copulas. So in this part, an Archimedean copula is defined through a generator function phi that is continuous, strictly decreasing, and convex. So we can write the copula C's like this. So the phi inverse is the pseudo inverse of the generator function phi. And of course, depending on the choice of the generator function, Archimedean copulas can exhibit both lower and upper tail dependence. So the only differences between those will be this generator function. Well, maybe not only the difference, but probably the biggest difference. Probably. And in this part, let me continue with Gumbel copulas, which is this one, finally. Gumbel copula is defined through its generator function. So in this part, phi of t will be equal to negative log of t to the power of theta, while theta is greater than or equal to 1. And the Gumbel copula can be expressed as like this. Here, the theta is the copula parameter. For the Gumbel copula, it is greater than or equal to 1. And when it is 1, when the Gumbel copula parameter is 1, it corresponds with the independent copula. However, when this parameter increases, the dependency also increases too. So I have another nice image. In this part, well, there's a tricky part in this image. They are not all one-to-one cubes, except for this first image. In the second one, we have 2 units of information, and then it goes till the 60 units of information, let me say. So at this point, when the Gumbel parameter is increasing, we can see this string-wise part, known as the upper tail dependence. It means that we are looking for the relationship of 2 variables when they have extremely big values. So Gumbel copula does not have a lower tail dependence. It does not work with smaller values, but with very big values, let me say, while the random variables takes these extreme values. And also maybe mentioning the tail dependence might be the right time right now. So the tail dependence characterizes how 2 random variables behave at extreme points, as I had just mentioned. And it is generally used in finance and risk management, etc. So I was looking for some blog posts. Sorry if it's very old post, sorry. But I think it's a good example to understand those type of differences. In this part, since Clayton copulas have left tail dependence, it means that when we move to the smaller values, the variables becomes more correspondent, let me say. And also, let's go back to the Gumbel copula again. So it has an upper tail dependence. So I have probably written this 3rd time, I don't know. So the parameter of the upper tail dependence is shown as lambda u, or in some papers, it is also shown as lambda plus. So lower tail dependence, as you might guess, it is lambda minus, whatever. So for the Gumbel copula, what we will use is the result of this equation. So lambda u will be this one, and this theta is the parameter of Gumbel copula. Gumbel copulas do not have a lower tail dependence. And let me also introduce you another topic known as the conformal prediction. So till that time, what we have done, let's look at this. So we try to understand the relationships between 2 variables while they are taking the extreme values, because we have introduced Gumbel copula. And from now on, in order to understand the confidence level, let me ask you this meaningful question. So which one would be more meaningful if I ask you about the today's weather? If I say that the today's weather will be between 0 centigrade degree to 50 centigrade degree, you might probably say, okay. So, but if I say that somehow narrow and meaningful interval, you might infer many informations about that. So if I say that the weather will be between 23 centigrade degree to 27, you can say that, okay, I have experienced this type of interval in my life, so I know I don't need any jacket, etc. So you can infer much more meaningful information. And prediction intervals are commonly used to assess whether the predicted data points have a reliable range of uncertainty. And overall, especially in the machine learning applications, what we want is that machine learning models should not give wrong predictions with high confidence. At this point, maybe while also mentioning the interval, the coverage topic might be helpful for you to understand. So let's say we are doing a classification problem, we are solving this type of problem, and the most likely class is cat. So we have imagine that many pictures of some animals, and the most likely class is cat. But after conformalizing this type of set, we can also say that it can be a lion or maybe a hamster too. So these two are they are showing somehow a high probability also too. And for the points of prediction, maybe using radius might be informal, maybe informative to understand the confidence interval too. And in time series, maybe you can also guess from this image, you can understand it. Somehow assigning some confidence intervals and benefiting them might be helpful because they are showing that probably this is the 90% interval that the prediction can occur, etc. And also let's mention the psychological part, like how confident you are, but not the psychological. So in every predictions, what we want is this equality. We want our predictions to be equal to the real observations. But how can we compute this? So how we can understand, how we can be confident that this equation is true? So so in order to do that, let me introduce you a prediction set. So let xy's and yi's be the independent and identically distributed feature and response pairs. And since the conformal prediction uses past experience to determine precise levels of confidence in their predictions, our main aim is to produce the y label, the y value, yn plus 1 for a new test data point xn plus 1. So we define the prediction sets C hat like this. So it's a mapping from X to the subset of Y with this probability. So by the way, this alpha is the error level, and generally it's like a residual or error level, let me say. Generally, we want it to be very close to 0. By the way, this states that the probability of the true label yn plus 1 being contained within the prediction set is at least the desired coverage rate. Alpha is the error level, and 1 minus alpha is the desired coverage rate, we can say. And also, maybe mentioning the quantile might be also important in this point. The Q is the 1 minus alpha quantile, so desired coverage quantile of our data. Let's say you have B numbers, S1, S2, S3, and they goes on to SB. If you want to find the 1 minus alpha quantile of those numbers, we will use this equation. So this is the desired coverage level we want. This is data set. And we are trying to find this quantile of this data set. So as a result of this equation, what we will get is the minimum Q values that met this condition. This is known as the indicator function, by the way. If this condition is met, it will automatically give us 1. And if it doesn't, it will give us 0. And there is also a reason why we are dividing this by our data set, because what we want is the proportion. Yes. So overall, the aim is to find the smallest possible Q, such that we have 1 minus alpha portion of the data below Q. And let us consider a problem where f hat x is a prediction model that gives prediction for any input x. And let's look at the residuals. Maybe we can consider the residuals as the differences. So this is our predictions, and this is the real observed value. So the difference between those two will be our residual. And then we will define Q like this. Now we can form a prediction set using this quantile we have just found. So we want to find all output values Y. So this the result will be the Y values such that the residual is less than or equal to Q. And Q is already determined. And also we can write this formulation like this too. So this is the conformal, this is the confidence interval. As you might understand, this is the lowest boundary of this interval, and this is the upper bound of this interval. And also, let me mention the calibration set. Calibration is a process of adjusting prediction intervals in order to achieve the desired level of confidence or coverage. But what does it even mean? So if the prediction interval is too narrow, we can underestimate the uncertainty. But if the prediction interval, just like the example I have just here, if the prediction interval is being too wide, we are overestimating the uncertainty. So in conformal prediction, we divide our data into two sets, one for training and one for the calibration purposes. So imagine D1 having N1 data points and D2 having N2 data points. But D1 is for the training samples and D2 is the calibration samples. So we are using D1 training samples for model fitting, and we are using D2 calibration samples for finding the residual. So in this point, the data set we are picking will be from this calibration part, and then we find the quantile for those residuals, and we can build the prediction interval just like I have shown you. And also let me define a score function. So score function S will give us as an output that is called non-conformity scores. It's like a fancier term of residuals, but in conformal prediction we are using this non-conformity scores, meaning that it shows how output and input are somehow related, how they are fitted actually. And of course, as you might guess, this larger scores indicates worse agreement between X and Y. Of course, there are some exceptions. Maybe we may want to some conformal, non-conformity scores which are higher, especially in classification, but this is not today's topic. I don't know. So here's SI are known as the non-conformity scores. So by using this non-conformity scores, the residuals, we can build a prediction set like this. So what we want is to find the Y values such that the conformity score is less than or equal to the this thresholds. Also, we can use the formal definition of the quantile into this formulation. So Q hat is essentially the 1 minus A quantile, but with a small correction. Instead of using 1 minus A, we can use this part instead of because this is known as the adjusted level. And also let me continue. Okay. So I have only 2 slides, I guess, and one example I was planning to show in the board. So there's a theorem known as the conformal calibration coverage guarantee, and it's saying why it should be at least 1 minus alpha. And let me continue about this proof. So the non-conformity scores will be sorted like this. And when the alpha, the error rate, matches this condition, the Q hat should be picked like this. Otherwise, Q hat will be infinite, meaning that all the data points can be selected and they are true. So, yes, thank you.
Thank you for the great presentation. Are there any